Okay, so the integral test has one idea. It says, can we use integrals to test for convergence or divergence of a series? And the answer is yeah. Yeah, we can. Here's what's interesting. When you think about what an integral is, the integral adds up little rectangles of area, don't it?
Yeah.
Adds stuff up. Well, what's a series do? It adds stuff up. So we're going to add up areas and pretend they're like terms of our sequence. That's kind of the idea. Terms of our sequence, and if you add up the terms of our sequence, we have a series. If you add up little area rectangles, well, that's an integral. That's what that means. So we're going to use an integral to say whether or not our series is going to a finite number, or whether our series is going to an infinity, or whether it diverges. So, we pretend that our sequence is a function. Now I'm going to use x's in just a little bit. I'm going to just kind of give you the brief outline here. So we let our sequence, so the terms of our series, that's our sequence, we let our sequence be represented by some function. We say if f of n is continuous. It's got to be continuous. It can't have any breaks. Can't go to infinity like this. Can't do that. It's got to be continuous. It's got to be positive. And it must be decreasing. But if the function that we're using to represent the sequence from where we're getting our series is continuous, if it's positive, and if it's decreasing, then we can use that integral to show convergence or divergence of our series. So basically, then this and this this is where I'm making a little jump here. So I know I said f of n because it's based in terms of n, but really this would be a function in terms of x. Okay, just like we did before. I forget what we did with that. We used a function in terms of x with a sequence before. We're going to do basically the same thing here. We say, hey, if this is true, if this function is continuous, positive, and decreasing, then this series of a sub n and this integral of f of x from 1 to infinity, notice we start at 1, we're starting at 1, going to infinity, going to infinity, then this integral will have either the same result. They will both converge or they will both diverge. But either way, they will have the same result. So practically what we're doing is we're checking our integral to find out something about our series, which is a really nice idea. Again, the really basic idea is, well, integrals add up stuff, right? Series add up stuff. Let's just model our integral after our series and add the stuff up. Yeah, we're not adding up everything in between because we're not talking about real numbers with our series. We're talking about just positive integers. But the idea is the same. One more thing about this is the idea is the same because, I'll get to it in a minute. Another idea. Practically what's happening is that our integral is acting as an upper bound for our series. That's practically what's happening. If we know that our integral is going like this, so we can find the sum of this and it's a finite number, then naturally if this is an upper bound for our series is going to have to fit somewhere under here, right? Or on it, it doesn't really matter. But if our integral is an upper bound and that integral converges, goes to an actual number, well, then our series must also. The integral acts as an upper bound for our series if it's continuous, positive, and decreasing. So if you understand the concept behind this. Now a couple key notes that I want to tell you about. First key note. This will tell you about convergence and divergence if this is true, if you make this happen. It will tell you about convergence or divergence, but it will not necessarily give you the sum. So if you do the integral, and the integral equals some number, you go, hey, it converges. That's great. Is the number it converges to the sum of your series? No, it's not. It just tells you that the series also converges, but it doesn't tell you what the sum is. Are you very clear on that? Okay, so this will tell convergence or divergence. But does not necessarily give the sum. Of this series.
So
Secondly, say what?
it sometimes can be the sum?
Sometimes, but not necessarily. What is kind of cool, and we get this from this, we can sometimes cheat at this a little bit. You see, convergence or divergence is not affected by the addition or subtraction of a finite number of terms of your series. So if I take out the first few terms, or add to it some terms in the middle, convergence is not affected towards infinity, as long as it's a finite number of terms. I can't add an infinite number, but if I say, let's add 5 terms, or let's subtract the first 10 terms, the sum would be different. Are you listening? The sum would be different, because obviously I'm adding or subtracting. Yes, it's going to be a little different. But the convergence will not be different. And since this doesn't tell us about the sum anyway, who cares? It's going to tell us whether it converges or diverges. Not telling us the sum anyway, so whether we subtract or add a few terms to tell us whether we can go to the right number, tell whether this our integral is going to converge or not, to tell us whether our series converges or not, that's what we're looking at. So we can sometimes cheat at this because convergence is not affected by the addition or subtraction of a finite number of terms of our series. So basically, here's what this is saying. It says, we can judge the convergence of this series with this series. Here's what I'm talking about. So hopefully you understand this. Let's say that the first few terms of this series, are you listening? First few terms of this series don't really mesh up real well with our integral. Okay, we got a problem there or something, I don't know, just because of continuity or positive or decreasing, whatever. Specifically, like the decreasing part is what we go with. Typically the continuity is not a problem with our interval. Typically if it was, our series wouldn't happen, because if we had that issue, if we had a discontinuity here, we'd probably have a discontinuity somewhere in our series. Those terms wouldn't even make sense. But usually for us, it's going to be decreasing. Sometimes this decreasing idea doesn't work so well with these exact terms. So we say, well, let's forget the first few. Maybe we don't start at 1. Maybe we start at n. Here's what this is saying, folks. It says, I don't care how many terms you subtract. Can't subtract all of them, okay? But if you subtract a finite number of terms, say, I don't want to start at the first term, I want to start at the third term. I don't want to start at the first term, I want to start at the 7th term. I want to start at the first term, I want to start at the whatever, the nth term, big N. What that says is that, yes, the sum will be different. The sum will be different. Don't care about that. It's not going to give us a sum anyway. But the convergence or divergence will not be different. Does that make sense to you? This is the idea. Sum will be different. The SUM, sum, will be different, but the convergence will not. So, if our integral is affected by this, we go, man, those terms aren't so great. Let's make it start a certain place, and therefore we can start our integral at a certain place and tell us something about our original series. This is the plan. You guys want to see the plan in action? You want some examples? Does this make sense to you, the theory behind it? It's kind of interesting, right? Let's do a couple real fast ones just to get our feet wet. Okay, one more recommendation. I know I've said this before, but I'm going to say it again and again. Please do not forget about the divergence test. Now, none of these for us are going to be divergent by the divergence test because that's too easy for us at this point, but don't forget about that. Because on a test or a quiz or your homework or something, you look at that and you go, okay, the first thing I'm doing, first thing right off the bat, I'm taking the limit of this. If the limit of this as n approaches infinity does not equal 0, what do I know about this series? It's divergent. Don't even have to worry about it. There's not going to be a sum. Don't have to worry about the integral because it's divergent already. Here, so we take the limit. Is the limit of 1 over n squared plus 1 equal to 0? Yes. So it says we're sure, well, we're not sure whether it's convergent or divergent, but it fails the divergence test. It's not divergent by the divergence test. It might be divergent some other way, but not by that. Does that make sense? Do we know it's convergent? No, we don't know that. It's basically inconclusive. So here's what we do. First thing is, okay, well, it's not telescoping. Can't factor it, so it's not definitely not that. We can't break that up. Then we try the integral test, because you know what I see? I see, let's look at f of x equals 1 over x squared plus 1. I'm not using n. I know I did up here, but I'm not using n. I'm using the function in terms of x because what we're doing is we're modeling this function after this sequence. And we're saying, okay, basically, every term of this sequence is in here somewhere. A lot more terms besides these terms are in here, yes, but at least this contains all of these terms. Does that make sense to you? So we're going to say, if this contains all these terms, this will act as an upper bound for this sequence, provided it is positive, provided it is continuous, provided it is decreasing. So let's think about this. Is this always positive? Yes. Absolutely. It's x squared plus 1. So this is positive. Is it continuous? Yes. Since it's always positive, well, yeah, it's actually always continuous. Oh, but wait, one thing. Do we have to be continuous everywhere? We actually only have to be continuous on that interval right there. So it's continuous. Yeah. Is it decreasing?
Yeah. What keeps getting smaller?
It does keep getting smaller because this is a constant, isn't it?
Yeah.
So a constant by something that's going 1, 2, 3, 4, 5, it's decreasing, obviously decreasing. Now we're going to state this on the interval 1 to infinity because we don't care about anything else. We don't care about anything else because what we're trying to do is model this function on this series. This series starts at, hey, where's the series start at? So as long as this function is positive, continuous, and decreasing on 1 to infinity, we are good to go. Show of hands if you understand that concept. Okay, so even if this had been like, oh man, this is going to change something a little bit. -1. I'll show you something here real quick. Is this positive?
Not all the time, yeah. Not ever.
Is it positive on 1 to infinity?
No, not all the time.
Because you plug in 1.1, it's positive. Is it continuous? No, not at 1. So what you do is you go, hey, can I subtract a finite number of terms? Heck yeah. Let's start at 2. There you go. Is it positive, continuous, and decreasing? Done, okay? So we can do things like this. Now, we're not there yet. We're going to get there in the next couple examples. So the next idea is, shoot, if you know how to model this series on a function and you know it's positive, continuous, and decreasing, do you need to check for this every time? Yeah. You certainly do, and you have to show each one of them. Some are obvious. This is obviously positive, obviously continuous, and obviously decreasing, okay? Then what we say is, then this series and this integral from where to where?
1 to infinity.
Of 1 over x squared plus 1 dx, these two things, because of this statement, these two things will either both converge or they will both diverge. That's what this says. If this diverges, this diverges. If this converges, this converges. Do I know the sum? No, but it converges. Don't know what to, but it converges. Do you see it? That's why we did last chapter. What is that? Oh, no. It's an improper integral. It's an improper integral which you must show me appropriately how to solve. Do you remember anything about improper integrals?
Oh, yeah.
That's an infinite interval, 1 to infinity. We say, hey, b goes to infinity, take a limit of that. No problem. Do we know how to do the integral of 1 over x squared?
Yes.
How much is the integral of 1 over x squared plus 1? It's tan inverse. If you didn't know that, you could do your triangle, x squared plus 1. You could do your x over 1. Hey, tangent. Look at that, tangent. You have a secant squared in there somewhere. It's simplified. You get the integral of 1. That integral of 1 would be theta. Theta would be tan inverse of x. So this right, and look, you can look that up for our. I've done that example several times. So look that up in the video or in your notes. This right here is the limit as b approaches infinity of tan inverse x from 1 to b. Integral of this is tan inverse x. Going from 1 to b, no problem. We have a limit still? Yeah, of course we have a limit still. What's the next step? What are we going to do?
Evaluating.
Plug it in, plug it in. Sure, we got tan inverse of b minus tan inverse of 1. Now you better be able to tell me what tan inverse of b and what tan inverse of 1 are. You might want to have your unit circle out or have something out that lets you see this pretty easy. For me it's not a big deal because, well, of course, I know this in my head. If you don't know in your head, have a little cheat sheet when you're doing some of these problems, especially with our tangents. So let's think about tan inverse of b as b goes to infinity. Tan inverse looks like this. Tan inverse looks like that, where you have a horizontal asymptote here at pi over 2 and a horizontal asymptote here at negative pi over 2. So this is pi over 2. As tan inverse approaches, as b approaches infinity, tan inverse of b approaches pi over 2. Minus tan inverse of 1. It's pi over 4. Because tangent of pi over 4 equals 1, tan inverse of 1 equals pi over 4. Equals. Now, question. Did we get a number? This limit, this is why the limits are important. This limit tells you that the limit exists, right? This says the limit exists. Therefore, this improper integral was convergent. That's where we had that convergent, the first word, right? The first time we had that was in improper integrals. Because the limit exists, the integral is convergent. Because the integral was convergent, based on this function which was positive, continuous, and decreasing, which acted as an upper bound for our series. If this thing is convergent, tell me something about our series. Good. So both the integral and the series are convergent. Do I know what the sum of my series is? Is this the sum of my series? Not necessarily. I don't know. But we know that that series converges. Show of hands if you understand the idea of this. Kind of a cool idea, right? Let's practice a couple more examples. Get right into it. I'll try to do as many as possible in our time allowed here for you. Okay, so I'm still going to walk you through this because I know you guys are fresh at this. We're only in one example. So the first thing we do, first thing is, my goodness, take a limit. Take a limit. If the limit does not equal 0, the series diverges. Now, most of these I'm giving you here, that's not going to happen, but I want you to get in a habit of that. Is the limit of this thing 0 as n approaches infinity?
Yes.
Yes, it is. Constant over infinity is infinity, so the limit is 0. Does that make sense? That means we got to keep going with something. The something here is going to be our integral test. So we're going to base our function on our series in terms of x, of course. Then we're going to check for 3 things. What are the 3 things we must check for the integral test to work?
Positive, continuous, and decreasing.
For everything, or just a certain interval?
Interval.
Aha! So, is this positive?
Yes.
Not always. Not always. But I don't care about that. Is it positive on, where am I starting?
1 infinity.
Is it positive on this interval?
Yes.
Yes. Is it continuous on this interval? Notice that 1/2 would be a discontinuity. Does that make sense? Is 1/2 in my interval? Then I do not care. Is it decreasing on my interval?
Yes.
That's a constant over a variable that is growing bigger. Decreasing. Show of hands feel okay with that. Positive, continuous, decreasing. Well, then what we're going to do is say, since this function is positive, continuous, and decreasing on my interval, the same interval as my series, I'm going to take an integral of this. The integral will act as an upper bound for my sum, my series. If the integral converges, this thing converges. If the integral diverges, this thing diverges. So, let's take our integral. Where's our integral start?
1.
Yeah, same thing as this. 1 to infinity. So wherever this function is positive, continuous, and decreasing, that's where you integrate. Do you guys see how many times you're going to be using limits here? These are all going to be improper integrals. So we're going to have a limit as b approaches infinity from 1 to b of 3 over 2x minus 1 dx. Oh my gosh. It's an easy one. Tell me what we should do with the integral of 3 over 2x minus 1.
Pull 3 out, substitute.
Pull 3 out, do a u sub. Very easy. If we do a u sub, we're going to get u equals 2x minus 1. Du equals 2x dx. Sorry, 2 dx. du over 2 equals dx. So, long story made real short, we have a limit as b approaches infinity of 3/2 integral 1 over u du. Well, that's a limit. I'm going fast here. Is that okay with you that I'm doing these integrals really quickly?
Yes.
Just because, well, frankly, I mean, we should know how to do all those anyway. You guys okay with this one so far?
Mm-hmm.
We go, hey, you know what? 2x plus 1, 2x minus 1 is our u. So we have 3/2. Pull it up front. Integral 1 over u, no problem. Du. Integral of 1 over u is ln absolute value of u. Now, tell me something. When I plug in my 2x minus 1, do I need the absolute value here?
Yes. Well,
From
from 1 to 0, always.
Think about my interval. Do I need the absolute value here?
No.
No, I don't. What I do need to do is evaluate from 1 to b and then take my limit. So let's do that. This would be a limit as b approaches infinity of 3/2. You know what you can do? You can even pull the 3/2 all the way out front if you want to. You don't even need it here. The constant can be pulled out in front of the limit. So let's do that. Let's have 3/2 out front. We'll have ln of 2b minus 1 minus ln of 2 minus 1. I gotta make sure you guys are okay with this before we go any further. Are you guys okay with this one, Patrick?
Because it's always positive, don't you never need the absolute values on any of them?
That we never need.
You know what I mean, it's a positive.
I don't know how to answer that one,
English
man. You know, I can't. I'm not going to make an absolute statement there. It's going to have to depend on what you have. What if you had x's over x's? I'm not sure. Okay. I don't know how that would work there. I'm not going to make an answer. I don't know. What I want to know is, are you okay making it this far?
Yes.
This is exactly the same stuff that we've done already in this class. Let's see what. Pull out 3/2, of course. That's, you know, we've been doing that for a while. So 3/2 up front. Tell me, what's 2 minus 1? What's ln of 1?
0.
What's b here? Going to infinity. What's 2 times infinity? Infinity minus 1. What's ln of infinity? Is this integral convergent or divergent?
Divergent.
This thing is infinity minus 0. That's infinity times 3/2. This is infinity. Therefore, this integral is divergent. Tell me something about the series. Is the series going to be divergent or convergent? That's interesting because it said the integral acts as an upper bound. It also acts as a lower bound. It acts as a bound. So the integral is the bound for our series. It's either an upper bound if it converges or a lower bound if it diverges, which is really neat. Therefore, the series also diverges. And this is exactly the way you state it on your homework and you test. You say, the integral diverges, therefore the series also diverges. You don't just end it with diverges, you make a statement about the series. You say, okay, so they're both convergent or they're both divergent. You say, because this one diverges, the other one diverges. Make some sort of a statement like that. Show of hands feel okay with this one. Tell you what, I'm going to talk about one more thing. We're not going to finish this, but I want to show you something while we're super fresh on this material.
Minty fresh even.
Minty fresh. Calculus fresh.
COVID.
Aqua fresh. Okay, so this is the first time we've had an n function over an n, well, not function, but an n over an n. The first thing you would do here, check your limit. Now, if you did L'Hopital's, you're going to find out that this limit does equal 0, but you would check by the divergence test first. Are you with me on that one? Always check that. Secondly, you go, okay, well, you know what? I know that this series, if I model this function after that sequence, and I determine that the integral of this function is convergent, this series convergent, divergent, this series divergent. As long as this is positive, continuous, and decreasing. Now let's talk about those three things and then we'll end for today, okay? So, is this positive?
N should be X's.
Oh, I'm sorry, thank you. Yeah. Yeah, my bad. Good save, good catch. Not minty fresh anymore. Tepid and rancid, whatever. F of x equals ln x over x. Is it positive?
Yes.
Is it always positive?
No.
No. Is it positive on this interval?
Yes.
Yes. After 1, ln of 1 is 0. After that, it's positive. Over something that's always positive, after 1, you'd have something that is positive. Is it continuous? The only discontinuity here would exist at x equals what? 0. That would be discontinuous for both of them, actually. After that, it's continuous. Is it decreasing? This is not an obvious one. Obviously decreasing. Here. Obviously decreasing. That's a constant. That's over a number that's growing. That's decreasing. This one, not so obvious. This time, you're going to have to check for decreasing. So here's our check for decreasing. You must show these things. Show decreasing. How I would show decreasing with a function, man, I would take the derivative of that function. Do you remember doing that? Man, we just did that stuff, right? To show that this is decreasing. If it's decreasing, the derivative has to be negative. Decreasing means the derivative is negative. So if we do the derivative, it's low d high minus high d low, square the bottom, and away we go. So our first derivative is 1 minus ln x over x squared. You guys okay with that so far? Well, here's the whole thing. We're trying to show decreasing, correct? We're trying to show when this thing is less than or equal to 0. That's what we're trying to show. Now here's the whole point. Is x squared ever negative?
No.
Then this will only be negative when 1 minus ln x is negative. This happens when this happens. You guys okay with that one? Yes, no? Are you sure? Yes, yes? Yes, yes?
Yes.
Okay. If I solve for this, I get 1 is less than or equal to ln x. That's not good enough. I want to solve for x. Well, If I take both sides as an exponent of e to the first would be less than x. E to the ln x is x. So take e on both sides. Don't take e, that's bad for you. But put e on both sides, this is exponent of e. Here's what this says to me, and hopefully to you. What it says is that this function is certainly positive, it's certainly continuous. It will be decreasing as long as x is bigger than or equal to e. How much is e?
2.7 something.
Then what if I made this 3? If I said this is decreasing on 3 to infinity, would it be true?
Yes.
If it takes x being bigger than or equal to e to be decreasing, then the function will certainly be, then f of x is certainly decreasing on 3 to infinity. Because 3 is bigger than e, it said x has to be bigger than e. Well, 3 is bigger than that. Therefore, this is also decreasing on the interval from 3 to infinity. So our integral, where's our integral? Oh, see if you can put it all together. Where's our integral going to start?
3.
3. Not 1. It's not decreasing there. But just start at 3. This was the... This is the first thing that we talked about in one of those notes. It said that I can subtract a finite number of terms. Listen carefully to the last little bit, okay? I can subtract a finite number of terms. I'm subtracting the first term and the second term. I'm starting at the third term. I don't want to start at e, okay? I want to make this an actual integer that matches up with our series. I'm going to start it at 3. So, check positive, check continuous. You guys okay with the decreasing part of this? Derivatives have to be less than 0 for decreasing. So show it. Hey, look at this will be less than 0 when this happens, or when this happens. Take e on both sides. When this happens, x has to be bigger than e. Make it 3. 3 is bigger than e. Therefore, this will be positive, no problem. Continuous and decreasing on 3 to infinity. Start your integral at 3. We'll finish it up next time. So we're going to finish up this problem. So if you were with us last time, what you saw was whenever we have these series, and we can determine that our function that's based on our series is positive, continuous, and decreasing, we can take an integral of that function. And what that function does, it stands for a lower bound for divergence or an upper bound for convergence. Basically, it says that every term of this sequence from which our series is built is found in this function. Therefore, if the integral of this function, remember integral means add up stuff, if the integral of this function diverges, means the sum or our series is also going to diverge. If the integral converges, means the sum or the series is also going to converge. That's the idea that we have. Now, does the integral necessarily tell us the sum of our series? No, it doesn't give us the sum. It just tells us whether it will have a convergent sum or a divergent sum. That's basically the idea. So what we've done here so far is just, all right, let's call this function ln x over x. So we've modeled it on our sequence. We've determined, hopefully, obviously to you, it is of course positive. It's definitely positive. That's positive, and that's positive after 1. Therefore, positive over positive gives us a positive. It's definitely positive after 1. It's continuous. The only problem we would ever have is at 0. Since 0 is outside of our interval from 1 to infinity, no problem. The problem we came across with this problem was the decreasing. How we show decreasing oftentimes with our functions, take a derivative. If a derivative is less than 0, if a derivative is negative, that means that our function is decreasing. If a derivative is positive, that means our function is increasing for a given interval. What we're trying to show is that this function is always decreasing. Does that make sense to you? So we take a derivative. Our derivative, you should know how to do that. We say, okay, when is this derivative going to be less than 0? Well, this derivative is less than 0 when the numerator is less than 0. You see the denominator is always positive, so we can't change our sign. So it's always the numerator less than 0 for this example. No problem. Well, if the numerator has to be less than 0 for a derivative to be less than 0, that means that 1's got to be less than ln x. If I take e, both these sides as an exponent upon e, I'm going to get e to the first is less than e to the ln x. No problem. What that basically says is this. The derivative of our function will be negative when x is greater than or equal to e. That's the idea. Does that make sense to you? So basically it says our function is decreasing everywhere after x equals e. That's what it says. Well, then what we're going to do is we're going to pick some number after this, after e. Well, what's slightly bigger than e? 3 is. We're going to say, well, you know what? Tell you what. Did you follow this logic down, by the way?
Yeah.
Decreasing means less than 0. That means this would have to be less than 0. That means this would have to happen, this would have to happen, and x would have to be bigger than e. That's what that says. Well, pick x equals 3, and then we know for sure that our function will be decreasing at x equals 3 and further, all the way to infinity. Show of hands if that makes sense to you. Now, the reason why we're allowed to do this, I gave you the statement last time, you can actually add or subtract a finite number of terms from your series, and the resultant of convergence or divergence will not change. So I know that our series, where's our series start? Where's our integral going to start?
3.
That's 2 terms difference, actually. So we would ignore the first term and the second term and start at the third term. Is the sum going to be the same? No, it's going to be different. Who cares? It's not going to give us the sum anyway. So it's just going to tell us, well, if I subtract a finite number of terms, who cares? It's going to give us whether this series is convergent or divergent anyway. Does that make sense to you? I think I explained it last time, but I wanted to make sure that you guys actually got to it. So we check positive, easy. Check continuous, easy on this interval. On 1 to infinity, that's both positive and continuous. Good to go. Decreasing, take a first derivative, work it down, find out what x has to be for this function to be decreasing. For us, it's anything bigger than e. Well, 3 is bigger than e, so let's make our interval from 3 to infinity. Now, what that says is that the integral of this function will have the same result as the series does. Either both will be convergent or both will be divergent. So we just got to do this integral. Fortunately for us, man, it looks so familiar. We've done that. That's an improper integral. So what's our first step with an improper integral, please? From what?
From b to 3.
Integral from 3 to b ln x over x dx. Now, of course, we're kind of past the whole integration phase of this class. We're still going to use it, but these are going to be quite a bit simpler than what you're used to. So think easy on these things right now. How would I do this? U sub. What's our sub? Yep. du equals 1 over x dx. Do you see it? It's right there. This is 1 over x dx. Therefore, we have a limit as b approaches infinity, the integral from 3 to b of, well, since I do my substitution, u equals ln x, so I'm going to have u. du is 1 over x dx. So du is this piece. Well, that was pretty painless. That means we're going to get limit of u squared over 2 as b goes to infinity from 3 to b. Show of hands if you feel so far so good on this thing. Now there's one little issue. What's the little issue that we have? Bounds are different from our variable right now. And since we haven't changed bounds, what we're going to have to do is we're going to have to resubstitute back in. So instead of having u squared over 2, we're going to make this the limit as b approaches infinity of 1/2. What was our u anyway? And take that from 1 to b. Sorry, 3 to b. My bad. Y'all okay with that so far?
Yeah.
Cool. Let's go for it. Is any of this hard for you at this point? No, we know how to do simple integrals. Not a problem. We know how to evaluate. So when we do this, we're going to have a limit. B goes to infinity. Looks like it'll be 1/2 ln b squared minus 1/2 ln 3 squared. Can you please tell me what's going to happen? What's going to happen with this limit? What's ln 3? No idea. But this is going to be some sort of constant, isn't it? So this is going to be some constant. How much is ln b as b approaches infinity? Remember, b is approaching infinity. How much is ln b?
Infinity.
What's infinity squared?
Infinity.
Times 1/2?
Infinity.
It's still infinity. Infinity minus a constant?
Infinity.
Tell me something about this integral. Is this improper integral convergent or divergent?
Divergent.
Why?
Because it's going to infinity.
Very good.
Does it
The
convert?
limit goes to infinity, therefore this integral is divergent. So, or the integral diverges. Now what we said was, because this function is modeling this series, it contains every term of our sequence, and it's adding stuff together just like our series would do. A series adds the terms. Well, the function basically adds up areas, basically the same thing. Since this is modeling this, it's an upper bound for convergence, it's a lower bound for divergence. What that means that is if our limit of our integral, if our improper integral diverges, tell me something about our series. You have to say that, okay? You don't just leave it divergent done. You say, so because the improper integral diverges, the series also diverges. So we say, so series of ln n over n also diverges. Quick show of hands, feel okay with this so far? All right. We'll tell you what, we got a little bit left to do in this section. I'm going to go through what is called the P-series. Go through that one. I'll do one more example of this, very similar to this problem, just to get our brains wrapped around it one last time. And then we're basically done with our section. So last little bit we got to talk about is something called the P-series. Here's what the P-series stems from. It says, suppose you got a series. Suppose it starts at 1 to infinity, and it's 1 over n to the p, where p does not change. The n is what changes. I want you to think about what this would look like, okay? Let's think about the first few terms just to get our head wrapped around what the world is a p-series. So notice, n's our index, right? N is what's changing. So would the p change? No, the p is going to be something like 2, 3, 4, whatever. P is going to be some sort of a positive number, not equal to 1. Well, it could be equal to 1, but then we have something that's not very interesting. So here's what happens. Actually, it is interesting. It's just something we've already covered. I should say it that way. Here's what happens. If I plug in 1, I'm going to have 1 over what?
N.
What is n?
Oh, 1.
What's 1 to any power?
1. Plus
Excuse me, I hope I didn't blow the speakers out on people's computers. That was loud. Well, if P's a power, power, cool. If P's a power, then I'm basically taking 1 over 1 to the whatever power. It's going to be 1. You see that? So I'm going to get 1 for my first term. Next, I'd get 1 over, what would my n be? 2. What would my p be? I don't know. It'd be whatever I tell you it is. It's going to be 2 to the p. Plus 1 over, what's the next one going to be? 3 to the what?
P.
Is the p changing?
No.
No, it's going to be whatever's defined in your series. 3 to the p plus 1 over 4 to the p plus forever. That's what a p-series does. It's basically taking your n and raising it to some power over under 1. 1 over whatever that happens to be. You guys okay with the idea of a p-series?
Yeah.
Now we're going to talk about when this converges and when this diverges. And basically we have everything in hand to do that. So this will always converge when something happens. And it will diverge when something happens. It's not going to be based on the n this time, because n is going to go through its sequence of numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9. It's going to be based on the p. So can you tell me, let's talk about the divergence first. Can you tell me when this series would diverge? What do you think?
P is negative.
When p is negative. You're right, when p is negative. There's also one more thing.
1.
What about 1?
1.
Now listen carefully. If p is 1, we would get 1 plus 1/2. You know, I'll write it over here. When p is 1, we would get 1 plus 1/2 plus 1/3 plus 1/4. Are you seeing where these numbers come from?
Yeah.
tell me what series that is? You should know.
Harmonic.
That's harmonic series. Very good. Is the harmonic series convergent or divergent?
Divergent.
Very good. So what we know is that it's not only negatives, but it's actually anything less than 1. Anything less than or including 1. Does that make sense to you? This is the harmonic series. So when p equals 1, it's divergent. If p is less than 1, well, the divergence test will actually show that to you. If p is less than 1, imagine this. This will actually work for both, but if you take a limit of 1 over n to the p as n approaches infinity. If you do that, and p is less than 1, we're going to get something that's divergent. For sure. Now, when will this converge? When p is
Greater than 1.
when p is greater than 1, you can think about this. If p is greater than 1, then 1 over n to the p, if you model this with a function, if p is greater than 1, this is positive. Yes? Any positive number raised to any power is going to be positive. This is continuous. N is never 0. It's also decreasing on the interval 1 to infinity. Because this will give you positive, continuous, and decreasing. We basically, I'm kind of skipping a step here, okay? You'd model this on the function of x to the p. F equals x to the p. This would be positive, continuous, and decreasing. If that's the case. Sorry, I'm trying to go faster than I really should. We'd model this on f of x equals 1 over x to the p. And if we did that, this is positive, this is continuous, this is decreasing. Therefore, by the integral test, also all the integral of this thing is always going to be, we're going to find something that converges. The integral test is going to tell us this is also convergent. So because of this. So, here's the thing one more time. If you have your p as less than or equal to 1, if you have your p as less than or equal to 1, what do you know about your p series? Harmonic series or anything lower than that for a power is going to diverge. If you have your p greater than 1, not equal to 1, 1's over here, okay? If you have your p greater than 1, what do you know about it? It's got to. Because any sort of a function like this where p is more than 1, your integral from 1 to infinity of 1 over x to the p dx, it's going to converge. You can do the limit on that if you want to. You do a limit from, of whatever your integral says, from 1 to b, 1 over x to the p dx. If p is greater than 1, this becomes a pretty easy integral to do. This would be like x to the negative 2, or x to the negative 3, or x to the negative 4. Are you with me on this one? Whatever's going to happen is you would add 1 to your power. That would give you at most x to the negative 1 if you add 1 to your power. Does that make sense to you? Because you'd have at least x to the second there. Well, that's not quite true. You could do this with decimals as well. But you'd have something that would still be a negative exponent. Does that make sense? That would be 1 over infinity when you plugged in that b. 1 over infinity gives you that 0 plus whatever constant you have, that's going to be convergent. So we have something that is convergent here. Show of hands if that made sense to you. Feel okay with it. Okay. So p series divergent, p is less than or equal to 1, p series convergent, p is greater than 1 by our integral test. And you can do this in general when p is greater than 1. Now, let me show you how this works and how nice this is. Trust me, you're going to like this. Here's where you're going to like it. I want you to consider that series. Firstly, is that a specific type of series that you know?
Yes.
Yeah. Is it geometric? No, it's not geometric. But we have lots of different types of series here. Is it a p-series?
Yes.
Very good. Hey, what's the p?
2.
Is 2 more than 1?
Yes.
Tell me about the series.
Convergence.
Bam. So you have to state something like this. You say, okay, this is a p-series. The p is 2, which is greater than 1, therefore this series converges. Do I know what the sum is? No. Do I know it converges?
Yeah.
Yep, that's what I'm asking here. Show a fancy view if you like that stuff. Huh? Don't you like that? Give me 30 of these on the test, huh?
100%.
100%.
So you think just go with the catch.
We'll kick some calculus in this class. Okay.
Or drinking.
Now you tell me, what type of series is that? It's still a p-series. Now you might want to write it as a p-series. So how in the world is that a p-series? Well, it's a series, n equals 1 to infinity, 1 over n to the, every type of root is automatically a power. This is a power. So we say this is a p-series. P is equal to, what's our p?
1/3.
Now, remember, this is not 0. It's not talking about negative. Of course, every negative p is going to give us a divergent series here, but it's not 0. It's less than 1. So even if we get something like 1/3, what's that tell us about our series here? This is less than 1 or equal to 1. You can put that too. Less than or equal to 1, therefore this series diverges. Is this making sense to you?
Yes.
Kind of nice little break from doing all the other stuff, right? Okay, we'll do one more. True or false? This is a p-series. True or false?
False.
True or false? It's a p-series. Well, wait a minute. It's not 1 over something.
Still a power.
You better be smart enough to do that, right? Okay, so if you have a negative power, you need to understand that this is the same thing as 1 over n to the positive pi power. That's a weird power, but I didn't say anything about p being an integer. I didn't say anything about that. All I said was p was a power. P is an exponent. If p is less than or equal to 1, your p-series diverges. If p is more than 1, your p-series converges. So is this a p-series?
Yes.
Yes, it is. You might want to write it as such. So it's a p-series. The p is, what's the p?
Pi.
Yeah, pi is about 3.1415926 something, whatever. I don't know the rest of them. But what I'm asking is that bigger than 1 or is that less than 1?
Bigger.
That's more than 1. So what does our p-series say about that?
Convergence.
Because we've done this in general, for p is anything bigger than 1, we can say that all the time. We don't have to reinvent the wheel and prove it every time. We know that if p is less than or equal to 1, that series is going to diverge. If p is more than 1, that series is going to converge. You better make darn sure that it actually is a p-series though, okay? So spend some time to really think about it. But if it is, goodness gracious, isn't that nice? So if you don't recognize the p-series, you have a lot more work that you're going to have to do, right? You do the integral test with this when you don't actually have to. We've done the integral test basically once and for all for this. This is why we talked about this stuff. If you didn't catch that, go back and rewind it, or watch the video again or something to catch that. The p-series here, really is an integral test over and over and over and over and over and over and over again. That's all it is. If you have any power, listen. If you have any power that's less than 1, any power less than like 1/3, what happens is that this would become x to the negative 1/3 power, correct? You would add 1 to it on an integral. That would become positive 2/3 power. When I let b approach infinity, that is going to approach infinity. That series is going, that limit's going to diverge. It means my integral diverges. That means my series diverges. Does that make sense to you? That happens anytime your p is less than or equal to 1. If it equals 1, you got ln x. we already determined that, well, this harmonic series diverges, so that takes care of the equal to 1. Anything less than 1, I'd have x to a negative p power. If p is less than 1, when I add 1 to it, x gets to a positive power. Does that make sense? What that means is that when I evaluate my limit as b approaches infinity, that thing's going to go to infinity. That's why anytime p is less than or equal to 1, I get a series that diverges. The opposite is true for convergence. If p is more than 1, I would add x to the negative p, correct? But if p is more than 1, when I add 1 to it, the power is still negative. That means I have 1 over x to some power. I don't care what it is. When b approaches infinity, that's going to approach 0. Make sense? Then I'd have a constant or something, therefore my integral would converge. That's the whole idea. So don't be doing integral test, all this stuff. It for sure would work, absolutely. But we've already done it like once and for all here, so don't reinvent the wheel. That's the whole point. Show of hands if you understand the point. Good deal. Tell you what, we're not going to do any more p-series. This is hopefully straightforward to you. I want to do one more kind of a little bit more advanced idea of series, show you what you can and can't do with it. Basically dealing with a little bit more with how to show decreasing, because the whole integral test says you got to have something that's positive, you got to have something that's continuous, and you have to have something that's decreasing. So I want to go through one more of those, and then we'll call it good on this section. You guys have any questions on the p-series at all that I can answer for you?
Yes, pretty much the only qualification for it, that your variable has to be in your denominator, just to any power. It can't be like added to anything, right? It just has to be like, variable to a power. Then you can use p-series in your denominator.
I didn't quite catch that.
Like, all right, like for p-series, yeah, your variable.
Give me an example.
Let's just say
1 over what?
let's just say 1 over n to the 7th plus 1. You couldn't use p-series on that.
Like that?
Yeah.
No.
It just has to be the
But
variable itself.
in the next section, we're going to cheat a little bit and do it.
Oh, all right, cool.
You want to see how?
Yeah, sure.
Is this for sure less than 1 over n to the 7th? It sure is.
Yep.
Does that converge?
Yep.
P-series. If this is always less than that one, tell me something about this one.
No, convergence.
Converges.
Oh.
Comparison test. That's the next section. Now, so yes, we are going to use the p-series a lot. Okie dokie, a lot. But we're going to normally do it, it's not as easy as what I gave it to you, we're going to normally do it as a comparison test. We're going to base our other series on something we already know about. We're going to base them on geometric series, we're going to base them on p-series, we're going to compare them to them. I'll show you how to do that. But first I want to do this example. Okay, so here's how we would go through this. I kind of did this for integrals for you, so I'll kind of show you how to do this for series as well, the thought process. The thought process is the first thing you check for is the divergence test. That would be the first thing you check for. In this case, the divergence test is going to show you, because you do a couple, well, L'Hopital's rules there, you're going to get a 0 out of that thing. Your divergence test tells you 0. What's divergence test say? If it's not 0, what happens?
Divergent.
If it is 0, what's it say?
Convergent.
Could be.
Maybe not divergent. Don't know. Undetermined. We got to figure this thing out. Okay, so for us, we already determined that. Next thing you check for, is this a simple series? Is this a geometric? No. It's not. Here's how you tell. Is it a number raised to the n under a number raised to the n?
No.
No, it's n raised to a power. That's not a geometric series. Does that make sense? Geometric is a constant raised to a power. This is not that. And you can't make it that. So no, it's not geometric. Is it a p-series? No. No. It's got to be 1 over something. That would be a p-series there. Does that make, or a constant over something? Because a constant you can pull out. This is not a constant. Does that make sense? So divergence test, well, it is equal to 0. So it might not be divergent. You got to check. Geometric series? No. P-series? No. And hopefully you just caught on how to check for that, because I just explained it right now. So what's our last option for us right now? Well, our last option is an integral test. So we got to look at this thing and pretend that we got a function of x, actually make a function of x that models this sequence. E to the 1 over x squared. Okay, in order for you to use an integral test, and you guys should all know this, in order for you to use an integral test, what must this function be on my interval for my series? What must it be? Positive. Very good. What else?
Continuous.
Decreasing.
The hardest one to show is usually
Decreasing.
decreasing. Positive is pretty easy to show. You just go, that's always positive because it's e to some power. That's always positive because it's squared. A positive over positive is a positive. It's definitely positive. Does that make sense to you? Continuity. Continuity is usually pretty easy to show. This is only discontinuous at 0. That's it. E is continuous everywhere. E to a power is always continuous. How about x squared? Well, it's always continuous except at 0. Do we ever hit 0 in our interval?
No.
It's always continuous. Hard one here is decreasing. Decreasing, you go, I don't know. How do you show decreasing for a function? You got to do one of two things. You got to show that a sub n plus 1 is less than a sub n, which is sometimes very hard to do. Or you take a derivative if it's something that you can take a derivative of. That's probably the easy way. If you have n factorials and things, do you know how to take a derivative of a factorial? Yeah, no. So you'd have to show that a sub n plus 1 is less than a sub n and go for that way. Show that it's decreasing. We did that once if you remember. Do you remember that with sequences? We did it. In this case, because I don't have any factorials, I have nothing horrible going on, and I can take a derivative of this, you can always show decreasing of functions by showing the derivative is what? Decreasing
negative.
functions always have derivatives that are
Negative.
negative. So if we can show that this derivative is negative for our interval, we show that this is decreasing on the entire interval. Now here's a little caveat. I showed this before. If it's not decreasing on the entire interval, is there a point where it is decreasing? If there is a point where it's decreasing, like last time, it was decreasing after e. Remember that? If there's a point, then we can subtract a finite number of terms from our series and get the same result. They're both going to converge or diverge. So it's just find out whether this thing is decreasing on a certain interval, and that's all about the derivative. So we're going to take the derivative. I'm going to do it very quickly. I know you guys know how to take derivatives, so if you do the derivative, remember it's not L'Hopital's, it is a quotient rule. It's low d high minus high d low, square the bottom, away you go. So low d high gives you x squared e to the 1 over x times negative x squared, times 1 over x squared. Negative 1 over x squared. Minus, so that's low d high minus high d low. Square the bottom, and away we're done. Spend some time on your own if you need to, and do that derivative on your own. I'm doing it really quickly, of course, but chain rule at work here. Don't forget about those chain rules. We'd have low, derivative of e to the 1 over x is e to the 1 over x times negative 1 over x squared by the chain rule. Keep the high one, derive the low one, you get 2x e to the 1 over x, and then square the bottom. So if we do this, we're going to get negative e to the 1 over x minus 2x e to the 1 over x all over x to the 4th. Let's make this a little nicer. We're going to factor out negative e to the 1 over x. If I factor out negative e to the 1 over x, what we're left with is positive 1 plus 2x. Can you verify that for me, that if I factor out negative e to the 1 over x, I get positive 1 plus 2x? Can you verify that?
Yeah.
Okay. Over x to the 4th. Tell me what we just found. Derivatives. Derivatives show decreasing when they are...
Negative.
Okay, so what we got to ask our question is this thing negative? Is this thing less than or equal to 0 on my interval? Well, let's think about it. All you're trying to do is show it. You're just trying to show that it is decreasing. If you can't show it, if it's not decreasing, you can't use this stuff. So hopefully it's decreasing for you. Let's see. Where does our interval start here?
1.
It starts at 1. Is this decreasing on 1? Well, let's think. True or false? This is always positive.
Yeah.
True or false? This is always positive if x is greater than or equal to 1. I don't care about negative numbers because my series doesn't start negatively. It starts at 1. So this is always positive, right?
Yeah.
This is always positive, yeah? Now think about this one. Is this always this without the negative? Is this always positive?
Yeah.
E to any power is always positive. So we got a positive, we got a positive, we got a positive. So you're telling me For any value of x, this expression will be positive, correct?
Yeah.
Are you sure?
Yep.
Me too, because that's positive, and that's positive when x is greater than 1. What would that do?
Negative.
So is this always negative for x is between 1 to infinity?
Yes.
This is positive for x equals 1 to infinity. This is positive for x equals 1 to infinity. This is positive for x equals 1 to infinity. Therefore, this whole thing is negative when x equals 1 to infinity. Because my first derivative is negative on this interval, because my first derivative represents increasing or decreasing, because my first derivative is negative on this interval, it shows that it is decreasing on this interval. That's the idea. That's the hard part. The rest of it's pretty easy. Show of hands if you understand that part, you feel okay with it. Can you go ahead and try to do the rest of this? Try to do that integral, okay? Go for it. See that you still have the chops to do integration. So because this function is positive, continuous, and decreasing, and because it's based on the sequence of the sequence from which we get our series, the integral from 1, whatever interval is, where it is positive, continuous, decreasing, our interval is 1 to infinity, where that happens. Our integral from 1 to infinity, e to the 1 over x squared dx will have the same result as our series. If this is convergent, our series is convergent. If this is divergent, our series is divergent. Of course, what we know is that this is an improper integral. We must treat it as such. Yay! Did you find the appropriate substitution? Not so bad, right? Not so bad. It's just a substitution. Most of these things are going to be just substitutions for you. Not horrible. If you do u equals 1 over x, then our integral becomes from 1 to b e to the u. Now what else happens? Let's see if you did this right. You guys okay with the u equals 1 over x? The reason why we see this is because the derivative of 1 over x is 1 over x squared somehow without the constant. So that derivative is up there. This counts as a 1 over x squared. So u equals 1 over x, du is negative 1 over x squared. Not a problem. Move the negative over here. Negative du equals 1 over x squared dx. That is this piece right here. So what is after my e to the u?
Negative b.
Cool. That's about the easiest integral I can think of right there, actually. So this is a limit as b approaches infinity of, what is it going to be? Negative, I like the negative what? From 1 to b. Now there's a problem here. Do we want to plug in b in 1 right now?
No.
If you do this, you're going to get a divergent limit. It's going to look like it's divergent. If you plug this in, what's the big problem with doing this? These aren't in terms of u. They're in terms of x, actually. So for us, we absolutely must substitute back in before we evaluate our limit. So this has to be negative e to the 1 over x. That's going to make a big difference. Did you catch that? You got to make sure you substitute in. Make sure your bounds match your variables. If your bounds are in terms of x, which they will be, your resultant from your integral better be in terms of x as well. So we need to make sure we substitute back in if we've done a substitution. Well, what that means is we got a limit as b approaches infinity, negative e to the 1 over b minus negative e to the 1 over 1. Let's see what we got. Firstly, did you get the same thing as I did? Good for you. That's fantastic. How much does this all make?
0.
this right here. This is going to be plus e somehow. Negative, negative, well, minus the negative is plus e to the first is e. How much is, let's do this, how much is b going towards?
Infinity.
How much is 1 over infinity?
0.
How much is e to the 0?
1.
Negative
1.
Negative 1 plus 1, 0.
So this whole thing equals negative 1 plus, or e minus 1. Now, do I care that it's negative 1 plus e or e minus 1? Well, not so much because it doesn't necessarily give me my sum for my series, but what's it tell me about this limit? This limit is equals number, doesn't equal infinity. It's not a does not exist limit. It converges. So what's it tell me about my series from where I got this? So by the integral test, this is convergent. So this converges. So my series also converges. And that, ladies and gentlemen, is what the integral test does for you. It will have the same, the integral if your function from where you, that's based on your sequence is positive, continuous, and decreasing on an appropriate interval, sometimes subtracting some terms, sometimes not, finite number of terms. If that limit of your improper integral converges, your series converges. If that limit of your improper integral diverges, your series also diverges. Show of hands if that made sense to you. Do you guys have any questions at all on any of this stuff? Yes, no?
N squared, not n to the n.
What'd I do?
N to the n.
What?
Series.
In your series?
Answer. Oh, cool. Yeah. I just like ends, all right? Sue me. All right. Well, that's it for the. That's it for the integral test. Next thing I want to give you is the comparison test. We'll do the next one.
Is that 9.4?